Assalamu alaikum. In the previous lecture, we talked about the rotational energy level of diatomic molecule. So today we are going to discuss the energy level of polyatomic molecule. In polyatomic molecule, we have two categories of linear and nonlinear. The nonlinear molecule are further divided into asymmetric and symmetric top molecule, and the symmetric top molecule are further divided into spherical, prolat, and oblate molecule. So in today's lecture, we are going to discuss the rotational energy level of all these category of polyatomic molecule, and then at the end we will talk about the rotational spectra of the molecule. Here, first we discuss the linear polyatomic molecule, and fortunately, we have the same interpretation of energy level for the linear atomic molecule as that of the diatomic molecule. The only difference is the low and closely spaced energy level because of the higher moment of inertia for the linear polyatomic molecule, because the rotational energies are inversely proportional to the moment of inertia. So here we take the example of carbon monoxide and carbon dioxide. Carbon monoxide is a diatomic molecule and carbon dioxide is a polyatomic linear molecule. So here the moment of inertia of carbon monoxide is this one, and the corresponding energy of the first rotational state is this one, whereas the moment of inertia of carbon dioxide is this one, which is of course greater than that of carbon monoxide, and the corresponding energy of the first rotational state is this one, which is of course lower than the that of the carbon monoxide. Similarly, if we take the difference between the two energy states of carbon monoxide and carbon dioxide, so we see that the spacing between the two rotational energy states for carbon dioxide is lower than that of the carbon monoxide. The rest of the interpretation is exactly the same. So now we are going toward the nonlinear molecule, and unfortunately, most of the polyatomic molecule are nonlinear. So their rotational motion is quite complicated. Here we have a nonlinear polyatomic molecule. So what we do here that we resolve the motion of a nonlinear polyatomic molecule into three mutually perpendicular axes. We call it, for example, A, B, and C. So here, for example, this A, this is taken as the symmetry axis. We have B and C. So the motion of this polyatomic nonlinear molecule is resolved uh, about three perpendicular axes. The motion about A axis, the motion about B axis, and the motion about C axis. So the angular momentum would have three components, A, B, and C. And of course, we know that the angular momentum is quantized. So this is equal to J and to J plus 1 under root h curve. So so there is energy associated with each motion about A axis, B axis, and C axis. So the energy is equally are the energy distributed among these axes. So we have this is the energy contribution from the motion about A axis. This is the contribution of energy of the motion about B axis, and this is for the C axis. So in polyatomic nonlinear molecule, we have two categories. So we have asymmetric top molecule when all the moment of inertia are different from each other. And then we have asymmetric top molecule where the two moment of inertia are the same and the third one is different. So, for example, if we talk about the symmetric top molecule, So here is the energy, and if we put the two moment of inertia, for example, about B and C the same, so we have this situation, and then you come to this equation number 3. And of course, if A is the symmetry axis, so there is a particular orientation or quantized projection of the moment about the symmetry axis, so that we represent by LA, and that is equal to K H cut, where this K is equal to 0 plus minus up to plus minus J, and this LA square will be equal to K square H cut square. So here this J, K, they play exactly the same role in molecular physics as is played by L and ML in atomic physics. And of course, in atomic physics, we take the symmetry axis as Z axis, and here we take the symmetry axis as A axis. So when we talk about the molecular spectra, so we talk about the A axis, we talk about the um, uh, quantum number J, and we talking about the quantum number K, just like we talk about Z axis, L and ML in atomic physics. So here we have Li square plus Lb square plus Lc square is equal to J into J plus 1 H cut square. So Lb square plus Lc square will be equal to this one. And then we know that this La square is equal to K square H cut square. So putting the value of K square H cut square here, so we can have Lb square plus Lc square is equal to this one. And then in the equation number 4 on the previous page, we had the energy given as this. So here Lb square plus Lc square, so we can put this value over here, so we can have this relation, and then after the rearrangement we can have this equation number 6, which represent the rotational energy of the polyatomic nonlinear molecule. And here now we have two quantum number, the J and K. So if we remove the non if we remove the non-linearity, so K of course goes to 0, and we have only this portion, which is equal to the diatomic molecule. So, so we have the two categories. So if both these moment of inertia are the same, so we have the spherical shape. If IA is less than IB, so we have the this shape. This is known as the prolat. And if IA is greater than IB, so we have this shape. This is known as the oblate shape. So if you put all these values over here, so the energies will go on changing. So in the next slide, we are going to show that how the energies of spherical, prolat, and oblate shape are there. So this is the energy of a non-linear polyatomic molecule. And if we take the example of the spherical top molecule, where these two moment of inertia are the same, and the practical example is the methane. So if IA is equal to IB, so this portion goes to 0, and we have the energy equal to this one, which is exactly similar to that of the diatomic molecule, or you can say the linear atomic molecule. So a spherical top molecule has exactly the same energy level as that of the linear or polyatomic molecule or diatomic molecule. And of course, the only difference will be there in the spacing and the value of the energies. The next, we have the prolat shape, and for this we have the IA less than IB, and the example is the methyl fluoride. So if IA is less than IB, so this portion has a positive value, and there will be the energy will go on increasing as we go toward the higher energy state. So the prolat molecule has higher rotational energies as compared to the spherical uh, top molecule. Now we go to the another molecule, the oblate molecule, where we have the moment of inertia IA is greater than IB, and the example is carbon chloride, this one. So here this value, this IA is greater than IB, so this one is uh, less than this one, so this coefficient of k square will be negative, and of course the energy will go on decreasing. So this oblate molecule has energy less than the spherical molecule, and the prolate molecule has energies greater than spherical molecule. So what you can say that the spherical molecule has energy in between the prolate and oblate molecule. So, as we have discussed the effect of centrifugal distortion on the diatomic molecule, so of course, for a non-rigid spherical molecule, um, there's also a centrifugal distortion, and the general formula is this one. So derivation of this formula take quite long. So I have just put the formula just to tell you that there are factors regarding the centrifugal distortion. So all these coefficients with D, they affect the bond length because of the centrifugal distortion. And when we come to the asymmetric top molecules, so unfortunately, we don't have a general formula like this, which is for the symmetric top molecule. However, in practice, we have seen that an asymmetric top molecule has energies comparable, energy between the prolate and oblate molecule. So you can say that an asymmetric top molecule is a little bit distorted molecule shape of the spherical top molecule.